Okay, a student asked me to do a problem like this, talking about the ideal gas law. And so, in this problem, a chemical engineer must calculate the safe operating temperature of this high pressure reaction vessel, and it gives the dimensions of that vessel, which is a cylinder. It gives the pressure, the safe pressure inside, which is given in something called megapascals, and then it gives, for this reaction vessel, it may contain up to 1.38 kilograms of dinitrogen monoxide gas. Calculate the safe operating temperature that the engineer should use here. Okay, so we can do these types of problems, and this will have to do with the ideal gas law. Now, if we remember, the ideal gas law is that PV equals nRT. So pressure times volume equals the number of moles times the gas constant times the temperature in degrees Kelvin. And it's important to remember, for the sake of the gas constant, what units we need to be in. Okay, so N is obviously in moles. Pressure is going to be in atmospheres. Volume has to be in liters, and temperature has to be in degrees Kelvin. Okay, so one thing that's just a little bit tricky you'll see in this answer is that the answer we'll get will be in degrees Kelvin if we apply the ideal gas law, but we need to really keep in mind that it's asking for this in degrees Celsius. And so as we do some of these conversions, then that's what we have to do. Okay, so let's tackle some of these. Let's tackle pressure first. Okay, so pressure is given to us in 4.40 megapascals, and so we need to convert that into atmospheres. And so this is how I do it. You don't have to do it this way, but this is how I do it. That I have 4.40 megapascals. Okay, and I know that in 1 megapascal, by definition, mega is 10 to the 6th, that there are 10 to the 6th pascals. And I do have written down the conversion factor for pascals into atmospheres, and that is there are 101,325 pascals in 1 atmosphere. Alright, so when I did that math, then I think I got something like 43.42 atmospheres. Alright, so I do have, now I've calculated the pressure and I put that into atmospheres. Okay, so let's go to volume. Well, to make things difficult for us, they don't give us the volume of the cylinder, but they certainly can provide that. So the equation for the volume of a cylinder is going to be that the volume equals pi r squared times the height. So a circle times a height essentially is what that is going to be to give us the volume. Okay, so let's plug things in, and so the volume here is going to equal to pi, the radius squared. Now it's giving it actually in diameter, so half of that diameter is going to be 17.5 centimeters squared times the height, which is 42.0 centimeters. Okay, so when we do that math, let me just do it on my calculator here. So 3.14 times 17.5 times 42 equals, so I get 40388 centimeters cubed, which is the same as a milliliter. A centimeter cubed is a milliliter. And so I need, remember, the units have to be in a liter. So I know that there are 1,000 centimeters cubed in 1 liter. Okay, so if we divide everything through by 1,000, then that will give us 40.388 liters as the volume of that cylinder. So I've got pressure in atmospheres now. I've got volume in liters. R is given. We know what R is. We're trying to find temperature. So all we have left to get now is moles to be able to solve this problem. So I have 1.38 kilograms of N2O. That is what dinitrogen monoxide is. Okay, so I need grams because I need to get the molar mass of that. So I know in 1 kilogram there are 1,000 grams of N2O, and I know that there are 44 grams of N2O in 1 mole. Okay, so if I do that math, then that will give me 31.3636. Just give me a few sig figs. I'll worry about sig figs at the end. Okay, so I have my moles. So I have moles, I have my volume in liters, and I have pressure in atmospheres. Well, now I can use that ideal gas law to solve for temperature. Okay, so I know that PV equals nRT, and so if I do that algebra, I know that the temperature is going to be equal to PV divided by nR. And so if I plug everything into there, then I get, well, so for the pressure, I'm going to put 43.42 atmospheres. For the volume, I'm going to put times 40.388 liters. That's what I calculated there, and there is my pressure divided by the number of moles, which is 31.3636, and that's going to be times the gas constant, which is 0.08206. Okay, so if I do that, then I get, I believe, if I look at my calculator, 681.28. Let's just get me right there. Okay, now I know from sig figs as I look throughout here, whoops, got the, get back to where I'm supposed to be here. Alright, so if I get my sig figs right here, I look here, I've got right there 3 sig figs. I've been doing multiplication and divisions, so I know that I've got 3 sig figs that I need to worry about. And so remember, this is in degrees Kelvin, and I'm being asked in degrees Celsius. So if I subtract 273.15, which is how I convert from degrees Kelvin into degrees Celsius, then I get 408.28. My sig figs are going to be 3 right there. And so the answer that I get for this problem is 408 degrees Celsius. So that's how you do these. Remember, the tricks are, remember we're doing an ideal gas law. We need to convert everything, and that's kind of the pain. I know it's a pain, and I wish they wouldn't do that all the time. But we do have to convert these into the precise units, meaning that pressure has to be in atmospheres. Volume has to be in liters. This is in moles. The N is moles. Temperature has to be in degrees Kelvin, and that's because of how we're using R. We're using 0.08206, which requires those particular units. Okay, so that's how we would do this particular problem, and I think you can tackle all the others, which will either solve for pressure or volume or number of moles, or as we did here, the temperature.